We're here to talk about periodic properties. These are sets of, well, properties of atoms that vary in systematic ways, or at least semi-systematic ways, as we move through the periodic table. This is a really big advantage for us thinking about chemistry because it means that we don't have to memorize things like the properties of individual atoms. As long as we know how these properties behave in the periodic table, if I want to say I need something that is going to be a large atom, for example, I can just know where to look. If I want something that's going to be relatively easy to pull an electron away from, I know where to look in terms of the periodic table. And so they're very helpful for just keeping track of things and understanding or predicting what a particular substance might act like. Properties we're going to talk about here include atomic and ionic radii. That's just the size. How big is an atom? Okay, that's the easiest one conceptually to think about what it means. The ionization energy, that's a measure of how easy or hard it is to pull an electron away from an atom. Electron affinity is going to be a measure of how easy or hard it is to stick an extra electron onto an atom and make a negatively charged ion. Your goal for these should be to understand the variations in these properties and how they're related to electron configurations, okay? So not just to remember, okay, the big atoms live on this side of the periodic table or something like that, but to have some grasp in your mind of why that's true, because that'll make it easier to deal with things. Starting off with the radii, atomic radius, okay? So the size of an atom is mainly going to be determined by its valence electrons. Remember, those are the electrons that are in the outermost occupied shells or subshells, right? Because those are the electrons that are the furthest away from the nucleus, they're essentially going to define the size of the atom. Okay, if those outermost electrons are held onto more tightly, that's going to make the atom smaller. If those outermost electrons are very loosely held, the atom is going to, in turn, get bigger. Okay, your inner electrons or core electrons, like if I'm in a relatively high atomic number element, your 1s electrons are going to be very, very close to the nucleus. So they're not going to be the ones that are out on the outside edge of your atom. Turns out the atomic radius is easy to think about, but hard to measure, and in some ways hard to define. The reason for that is if you think about what orbitals look like, what those wave functions look like, pretty much all of them, as we go to long distances, they come back down to zero asymptotically, right? And that means there's not really a hard edge to where is the outside of an atom. An atom isn't really like a bowling ball or a billiard ball, right? It's kind of fuzzy around the edges. And so people make various definitions. Because of that, if you actually look up values of atomic radii, you have to be really careful to make sure you're looking at a consistent source, okay? Because there's different ways to define them, and you can see different numbers, sometimes significantly different numbers from different kinds of sources. So the figure that I put in here is one that's in your textbook, and here we definitely did get a data set that all comes from one way of defining the size of the atoms. In it, let's look at the axes. We've got the atomic number down here on the x-axis, and we've got the radius in picometers. Picometers is 10 to the minus 12 meters. Right, atoms are pretty small after all, and so the radii are in units that make these numbers be on the order of like tens between 50 and 100 for the most part. Okay, there's a lot of things in this graph, but let's take a look. The first thing is each different symbol and color on the graph represents a row in the periodic table, right? So down here, my first row is very small. It's got just hydrogen and helium, right? So this is hydrogen up on the top end of that, and then down here, that's helium. Right? If I keep going in my periodic table, in the next row, I get lithium up on the top. That's on the left-hand side in group 1. And down here, I get neon back over in group 18. Okay? And so what we can see in this graph is that for each row, as I go across a row from left to right, what's happening is that my atoms are getting smaller, right? Because on the top of each one of these, this is the group 1 end of things. On the bottom, those are the group 18 ends of the rows, okay? So this one is actually a little bit counterintuitive to a lot of people. People often think that the atom should get bigger as you put more stuff into it, and we can talk in a second. I'll explain in a second why this is true, okay? Notice the trend is very, very nicely behaved, right? It's pretty consistent throughout. There's a little bit of weirdness that happens over here. That's actually when we get to the so-called lanthanides, the F block elements, the ones that are generally drawn down here below the periodic table, right? And those cause some strange things to happen in that function. okay, in that size distribution. But all of the rows before that, the trend is very clear, right? As I go from left to right across the periodic table, my atoms get progressively smaller. As I go down a column in the periodic table, right, here's helium, here's neon, here's argon, and so on. So you can see as I go down a column, my atoms are getting larger. As I go across a row, they're getting smaller. Right? That's what the periodic table down here says. My size decreases as I go up and as I go from left to right. So that means the smallest atoms are up here. Small, really I'm writing an L there. And down here I have my big atoms. Right? And if you remember that, it's relatively easy once you get that idea in your mind to keep track of how the sizes should vary. So why is this? The part of this that's counterintuitive is the one where you go across the row from left to right and the atoms get smaller. You're putting more electrons in, right? And that often, if I ask this in a class question, people often say that they'll expect the atoms to get bigger from left to right, okay? The reason for this is as we're putting more electrons in, we're also putting more protons into the nucleus as we go from left to right across that row, okay? And when we do that, what happens is that, yes, as I go, I'm putting more electrons in that outer shell, but I'm also increasing the charge on the nucleus, and that just pulls those whole, that shell in, right? Imagine I'm in the, I don't know, the n equals 2, the second row of the periodic table. So I've got lithium on the left-hand side, I've got neon on the right-hand side. As I go across there, because the nuclear charge is growing from +3 at lithium up to +10 by the time I get to neon, that effect outweighs the part about putting more electrons in, and that's sort of why the atoms actually get smaller. When I move down a column, I'm going up by a whole n, right? I'm staying in the same sort of general electron configuration. Like if I go from neon to argon, I'm still at a p6 configuration, but I went from 2p6 to 3p6. That's a big change in the amount of stuff, and that makes the atoms get bigger as I go down the column. I'm going to talk about sizes for ions just a little bit, okay? Remember, ions, we can make positive or negative ions. Positive ions means we've taken an electron away. Negative ion means we've added an electron, right? To think about these, you generally, you can compare an ion to either its own neutral atom, or you can compare it to anything else that has the same number of electrons as it, right? As long so it's the same element, then they have the same number of protons. If it's the same number of electrons, then you can look at the protons, because the two things that influence the size are how many protons do I have, how many electrons do I have. In general, more protons will want to make the thing be smaller. More electrons will want to make it be larger, okay? So let's look at the picture here. You can see, first of all, on the left-hand side are all the metals, where for every single one of them, the ion is noticeably smaller than the neutral atom, right? So the way this figure is in the colored bars, so in this part, those are my ions, and here I've just got my neutral atoms. And the same for the others. You can tell that every single one of them gets smaller when I take the electron off of there. If you look at what ions these things make, lithium, sodium, the group 1 elements make +1 ions. That means they started off with an S1 electron configuration. We took out that last electron, right? So that means we removed the outermost shell and went back to the previous group 18 configuration. That makes it get quite a lot smaller if you just look at how much those shrink. Group 2, I'm taking out 2 electrons starting from something that ended in S2. I take out both of those S electrons, and again, I get a much smaller ion. Go to the right-hand side, look at the anions, negative charges. Every single one of those, when I put the extra electrons in, it gets bigger than the neutral atom, okay? That should make sense. It's a little bit confusing to some people because it says, well, when it went across, you said more electrons went in and it was getting smaller. That's true, but when it went across in neutral atoms, protons were being added to the nucleus, right? When I take O and make it into O2 minus, I added 2 electrons without putting the extra protons in, right? And so O2 minus, if you look at the numbers here, is a lot bigger than neutral oxygen. These are, again, these are radii and picometers again. Okay, just like the same numbers as were in the previous graph of things, Okay, so if I wanted to, I could compare things that have the same number of electrons, like O2 minus here and F minus. Those have the same number of electrons. They both have 10 electrons at that point, right? And you can see that O2 minus is a bit bigger than F minus because F minus has one extra proton compared to O2 minus, right? So that shrinks it down. Similarly, down here, the sulfur ion S2 minus is bigger than Cl minus by at least a little bit, right? And that we can attribute that to the fact that there's protons there. That effect is obviously pretty small, okay? Next on my list of properties is the ionization energy. We've actually kind of talked about this in a couple of different places already. We talked about photoelectron spectra, right? Where what we call the binding energies in photoelectron spectra, the smallest binding energy is really what we're now going to call the first ionization energy, right? So it's officially the amount of energy required to remove an electron from a free neutral atom. Okay, so if Z is just my element, my atomic number, say, to represent that, I supply some energy, that energy does work, and it pulls the electron free from the atom to make the positive ion, Z plus here, and the electron, right? So my charge is balanced. I leave the positive charge behind on the ion that I make. I get the negatively charged electron coming out of there, okay? So that's what the ionization energy is. Let's look at how the ionization energy varies as we go around in the periodic table. Okay, I think I have another graph for this. Here we can see it's got a pretty good general trend, although it's got more erraticness in it than, say, the size one did, right? So if I look at these, on the top here, the elements are actually labeled, right? So here's helium, neon, argon, krypton, and so we can see that as I go across a row that says here's hydrogen up to helium, here's lithium through neon, here's sodium through argon. As I go from left to right, my ionization energies are definitely increasing, right? That should make sense to us, because think about the fact that the elements on the left-hand side, those are the things we've been saying make positive ions all the time, right? We said, well, sodium is going to make Na+, and so on, right? That's because it's easy to take an electron away from those atoms. It doesn't cost much energy. We don't see like helium plus because helium's ionization energy is very, very high, right? It would cost an enormous amount of energy to pull that electron away from helium, which is why we don't actually see that species exist. Okay, so if I look going down a column, I can see that my ionization energies are getting at least a little bit smaller, right? So here's helium to neon to argon to krypton, and I'm going down at least a bit. Here's lithium, sodium, potassium. You can see that trend is not very pronounced, but they are going down at least slightly there. Okay, and so that is the labeling that's on our periodic table says the large ionization energies are up here, and the small ones are down there, smallest, right? In fact, all the things on the left-hand edge have really small ionization energies, right? These, my graph here is again atomic number this way. These are measured in kilojoules per mole, and you can see they range from about 500 up to a couple thousand in kilojoules per mole. Okay, so that's how much energy it costs to pull the electron free from the different elements. There are a couple of places where there are some regularly occurring exceptions here, right? If you look here and here, you see some places where things turn downward, okay? This is rationalized usually by saying that if I have a filled subshell or a half-filled subshell, it somehow is a little bit more stable, right? So think about where these happen. Beryllium to boron, beryllium's electron configuration ends in 2s2, right? So when I get to boron, then I have 2s2, 2p1. And so when I'm at 2s2, I've got a filled s subshell. The single electron in the p says the ionization energy goes down a little bit. Is that a really huge deal? Not really. Nitrogen to oxygen, this one matters a little bit just because nitrogen and oxygen are pretty common elements. Nitrogen is at p3, right? 2p3. Oxygen is the first one where we have to then put a second electron into one of those 2p orbitals, and that one has a little bit smaller ionization energy. I don't want you to get overly worked up about those exceptions, okay? It's true they happen. It's nice to be at least vaguely aware that they're in there, but I'm much more interested in having you get familiar with and fluent in the general trends, and so I don't want you to be thinking about where there's those little glitches if you're answering questions that are just expected to be based on looking at the periodic table. We can also think about higher ionization energies, second ionization energy or a third ionization energy, and so on. All right. Those are going to be defined in a way similar to the first ionization energy, except we're going to start with something that's already got a positive charge. So the second ionization energy would be defined like this: is take the Z plus cation, measure how much energy we have to supply to pull an electron away from it to make Z2 plus. Okay. For every element, the second ionization energy is always going to be higher than the first ionization energy. And that's just because now I'm trying to pull an electron away from something that's already got a positive charge on it. That's always going to make it more difficult. Let me draw myself some orbitals over here. I'll leave out the 1s's, I think. I'll do 2s, 2p, and 3p. I think that'll be enough to 3s. Wow, I'm really having a hard time here. Sorry. And I'm going to draw myself 2 sets of these. And what I'm going to do is I'm going to write out both sodium and magnesium because they'll help for some explaining here. And if I put the electrons in to get to sodium, sodium ends in 3s1. Magnesium is right next door. So it's going to be 3s2, right? If I were to measure the first ionization energy of either one of these things, it's going to be pretty small, right? They're over on the left-hand side of the periodic table. And so they should have small ionization energies. If I were to go back to the previous slide, we can see that both of them, they're down here. So they're at pretty small values as the overall graph goes, right? So suppose I've already taken one electron out of each of those things, okay? So now I'll just go ahead and maybe do that. I will say if I take an electron out of here and take an electron out of there, now I've got ions, right? Now I have Na plus and Mg plus. Okay, if I want to take another electron out for sodium, it's going to have gotten much more difficult, right? Because now, instead of being able to take an electron out of the 3s subshell up here at a higher energy, I have to reach down into the next subshell under that, the 2p, and I have to break up that 2p6 arrangement, right? So I have to break into the previously filled 2p subshell, right? That's going to be a much higher energy, okay? Whereas in magnesium, I still have another 3s electron out here. So the second ionization energy for magnesium is going to be higher than the first, but not enormously so. If I went to a third ionization energy for magnesium, then it would jump up tremendously, right? This actually is why sodium ends up always forming Na plus, but not Na2 plus, because Na2 plus would be very difficult. Magnesium forms Mg2 plus rather than Mg plus or Mg3 plus because it's got 2 electrons that are relatively easy for it to lose, okay, to pull out of there. So it's got 2 relatively small ionization energies. If I measured the third ionization energy for magnesium, it would again be a much larger number where, I don't know, the first ionization energies for those things are around 500 or 600 kilojoules per mole. The second ionization energy of sodium is probably somewhere approaching a couple thousand kilojoules per mole. I don't actually have the number with me, but it's going to go from being on the small end of that previous graph up to being up on the top end of things. And so it's a very big change that happens when we have to break into that previously filled subshell underneath. We're going to talk about electron affinity a little bit because we'll need this idea when we talk about forming chemical bonds. Electron affinity is a way to try to measure the tendency to form anions. The language of defining electron affinity is much more convoluted than the other properties, so sorry for that. There are two ways we can write a definition of this. We can say it's the amount of energy required to add an electron, meaning I take, if I have to put energy in, then that would be a positive electron affinity. If I have to shove the electron into the atom, meaning as soon as I stop supplying energy, it'll fly back out, right? Or I can say it's the amount of energy released on removing an electron from the anion. The energies, the electron affinity is defined this way because it's consistent with signs for how we do thermodynamics when we talk about energies. What it's not consistent with is how the word affinity works in normal language, okay? Because with these definitions, if the electron affinity, if the atom actually wants to add the electron affinity is going to come out to be negative, okay? And that's a little bit weird. Why is it negative? If the atom wants the electron, that says, suppose I have my atom here and I bring up an electron into some proximity. Suppose my atom is like fluorine that wants to make F minus, right? If my electron gets close, the atom is actually going to pull it in, right? And so that means that I would actually have to be pulling if I wanted to keep the electron out of there. So the amount of energy I have to supply to add the electron is negative. That's a little bit hard to get your head wrapped around. So take some time and think about that. The take-home message is that we want the atoms that will form anions are going to be the ones that have negative electron affinities, okay? I'm going to put up a graph of this, and it's always a little bit awkward, this particular graph, because it's just not very useful, okay? So let's look at some things on here. First of all, we can see that fluorine and chlorine, two things that we say are regularly making F minus and Cl minus. Sure enough, they're down here at the most negative values, okay? So that matches what we said should happen. Oxygen makes O2 minus, sulfur makes S2 minus, and they're down here as well. The other thing I want to comment on is you see a lot of elements up here written as with values at 0. We go round and around every time we revise the book thinking about how to depict those. Those are really things for which we basically can't measure the electron affinity, okay? Because what that says is that it's, if you can't add the electron, if the ion is not stable, then if the electron affinity were positive, it's not possible to get the electron to actually stay in the atom. That says as soon as you stop pushing energy in, the electron flies back out, right? If it's impossible to make your anion, then the measurement of the electron affinity is actually trying to measure how impossible it is, right? And you can't do that, right? Something's impossible, you just can't do it. It does seem like some impossible things should be arguably more impossible than others, but you can't really do that as a measurement, okay? And so those things that say they're at 0, they're not really to be trusted. So as you can see from the graph, the electron affinity is not nearly as nicely behaved property as even the ionization energy, right? Because the points are kind of all over the place. Nevertheless, it is kind of useful as a measured thing that can tell us that the elements over here in this part of the periodic table are the ones that are going to form anions. And we do see that by the things that are down there having negative values. Talk about one last thing, which is sort of a periodic property, and that's the idea of elements being metals or nonmetals. Okay, people have told you for years and years in school that metals have certain sets of properties, right? They're good conductors of heat and electricity. They are malleable and ductile. Those two words always travel together, right? Well, they look like metals. They're kind of have a shiny appearance, okay? The periodic table kind of groups them all together, you can see, because in this periodic table, which I sometimes stick in when I just need one to put in slides, the metals are in the blue color, right? And you can tell that they are the entire left-hand side of the periodic table, pretty much. The nonmetals are the pinkish ones over there towards the top and right. And then there's some orange ones which are labeled here as metalloids, sometimes always marked as, sometimes also called semi-metals. Those are things that have some aspects of metallic property and some aspects of non-metallic property, right? So in terms of electron configurations, what can we say? Metals are things that tend to have relatively few valence electrons and that will tend to lose their valence electrons and form positive ions, right? Nonmetals are things that have relatively more valence electrons. In general, they will tend to take on electrons to fill in the rest of their valence shell. Okay, metalloids again being in between. One thing that's a little weird about this periodic table, like a number of them, has hydrogen both over here and over there. Okay, hydrogen is colored in here as a nonmetal, which it certainly is in its normal incarnation. I will say there are some experiments that suggest if you take hydrogen and hold it at incredibly high pressures, enough to get it to solidify, that it actually forms a solid that does have reasonably good electrical conductivity. It's ridiculously hard to do that because you essentially have to trap some hydrogen between some diamond pieces in order to be able to sustain a high enough pressure to get it to stay a solid and be able to make that measurement. But people have done that, and there is growing evidence that solid hydrogen would in fact act like a metal and make it seem more at home in that first column of the periodic table.